We spent weeks trying to figure out whether to buy a grid-powered RV air conditioner or one of these abundantly available 12-volt air conditioners on Amazon or eBay. Follow me into a bottomless rabbit hole if interested. Grid-powered air conditioners, and I'm talking about the ones mounted on the roof of the RV, can cost twice as much per BTU compared to a 12-volt unit. And since they are mounted on the roof, they are also much more audible in the interior because their compressor sits in that housing, vibrating on the roof surface, which makes it very audible in the interior. Our 12-volt air conditioner, on the other hand, silently running on our battery bank, can be mounted anywhere in the vehicle. It runs all night just on battery power, and we can cool our cabin while driving the RV. Best of all, depending on your BTU needs, how large your vehicle is and how much cooling performance you really need, this is a much better deal because you're not only getting an air conditioner for the price of a roof-mounted AC unit, you're also getting a battery bank. And yeah, the easy part is to buy a random battery pack and a 12-volt air conditioner. But the hard part is to make sure our alternator will not melt when using the air conditioner while driving, and also to build a good quality sound battery pack. And that is what this video is all about. And in this video, I'm also gonna share with you how we added a plate heat exchanger to extract the waste heat out of our air conditioner and use it to heat up our shower water. Super exciting stuff, all coming up right now. So our first thought was to add a grid-powered roof AC unit onto the RV and provide power while we are driving through a 4 kilowatt inverter, which is connected to a lithium iron phosphate battery, and that would be charged up by the alternator of the vehicle while driving, right? Problem here is the original alternator in this vehicle or many other old RVs just has an 80 amp output, which is barely enough to provide a kilowatt, which would be the minimum of this air conditioner on the roof. But biggest problem here is to provide energy while at idle in a traffic jam or something like that. This usually reduces the airflow so much that these alternators overheat, and that's of course not a good option because they don't overheat, they just reduce their output to cool down, and that in turn would shut down the air conditioner and everything else in the system. Because yeah, if let's say it's at night or in a tunnel or something like that, then yeah, the total energy consumption is way above what this old 80 amp unit could handle. So that led to the idea to add a second alternator, water cooled, and these water cooled alternators are made for cases like that. They have a high output capability during idle and keep, or just slightly raised RPM and keep cool. That's why they are made like this, for exactly that reason. So now with our power supply figured out, we focused on the next big thing, and that is the air conditioner itself. And of course, a roof-mounted traditional RV AC is a great option on the campground, connected to shore power, and even while driving with a strong enough inverter and our alternator, there shouldn't be any problems. It should work. While driving, it most likely is very challenging to get the cold air from the back of the RV where the AC is mounted to the front, because we have fresh air entering through the vents in the cabin, and the cold air coming from the back would have to fight against that. So definitely not a good idea. And we thought maybe we could add some ducts to the roof-mounted AC and bring it to the front, but that would be incredible challenging, I think. And then we looked into underfloor units that are quite popular for boats in the marine world and bigger RVs. And these units look really good, like this one here. But they're, first of all, very expensive and quite hard to install. And the smallest one I could find is 16,000 BTU. That would be overkill for what we need. So that led us to the 12-volt air conditioners, and especially the under the dash units, which we decided to buy, or the one under the dash unit that we decided to buy. And this one is the one I tested in my last video to measure the real BTU output before we went through all the hoops to install it. We wanted to know how much does it really produce, right? Because all the videos online are quite, you never know if they're real or just a promotion. So yeah, if you're interested in that math, check my last video. The truth is, none of these units consuming 60 amps will ever reach 12,000 BTU. It's not possible. But they are actually quite efficient and produce around 7,500 BTUs, which is plenty for what we need. Yeah, also in my video, I learned that switching from authentic 134A to those 134A replacements that are very common on eBay and Amazon, and I think they're actually the only thing you can buy for environmental reasons. The potential 7,500 BTU output is basically cut in half. Evaporator freezing up and compressor overheating, so not a good option at all. In case you installed such a system in your RV and you're not happy, check what gas you pumped into the poor thing. You'll be glad you did. Now the next big mission is to decide what kind of battery we need for our system. A very difficult question, a balance dance between cost, weight, and efficiency or necessity. And nice view. And yeah, our benchmark was, of course, to run the air conditioner for at least one night, 8 hours with some capacity left in the morning to run our lights and whatever is necessary. So 8 hours times 60 amps, 480 amp hours minimum, and that would require at least two 280 amp hour lithium iron phosphate or two 320. But we ended up and decided to go for one 628 amp hour EVE battery because they had a special with a wonderful JK BMS. And also I would never recommend buying an off-the-shelf battery pack because all of these units come without compression, cell compression. And when you look into the warranty requirements of those cell makers, and especially how the cell makers themselves build a battery pack, it always comes with cell compression. You look how they build EV batteries or for commercial storage. They all have massive plates at the end and metal strips pulling them together. And it's very costly engineering and is weight and all of that. They do that for a reason. So be my guest to challenge that. But I truly believe it's a necessity. So here the battery we ended up buying. It came in a really nice metal housing with like network connections and all that and a display. The housing is really nicely made with bumper space around to protect the cells, which is, I think, a very good idea. It doesn't have any extra bumper on the bottom, which, well, we knew it, so we added a board at the bottom. It has a very nice fuse here, sturdy high current outlets. The wiring is nicely made, really everything is beautifully designed. A bus bar on top here, no, not a bus bar, but the balancing board with connections to the terminals. And also this BMS here is included of 300 amps. So in total we paid about 750 including the cells. This price is just for the box with hardware. Again, a very good investment and really good deal. Just briefly about the BMS. This comes with 2 amps active balancing, which is quite important for, especially for battery cells this size, because a regular passive BMS, they deliver maybe 200 milliamps, and if one of those gigantic 628 amp hour battery cells is out of balance or gets worn down with time, they're gonna have different capacities, and the BMS is going to struggle to keep this battery in balance. So that's why, to my opinion, it's really important to have active balance BMS. Again, this one provides 2 amps, or it's mentioned here. So this is the JK is one of the few really offering that much balancing current. And when those batteries are new, it's not such a big deal. But when they get older, it for sure is. So it's worth it to invest at the beginning. But the biggest point now, even this battery here comes without cell compression. And well, they claim it has cell compression, but it's not really mechanically sound, this whole solution. And we designed a concept to provide the proper 300 kilogram force to compress these cells, and that's where I'm gonna dive into now. I'm gonna explain you how we did that. So we built this battery pack, 650 amp hours EVE, and this is the casing they sell with their batteries, pretty nicely made, but it's lacking proper compression. It just comes with this simple sheet metal plate at the end that is retained with like 6 M4 screws, and that easily bends. The manufacturer, when you look in the data sheet of this battery pack, they recommend a compression of 3,000 Newton, and obviously this fixture cannot provide that. So we designed this compression system. It's quite simple, just 2 screws and pipes welded into the bottom, and then on top it's connected to 2 more pipes in the back, and then with some threaded inserts, thread bars, I don't know how you call these, and properly torqued to 2 Newton meters each screw, and that should be exactly 300 kilogram of force. And with that we hope to avoid the expansion effect of the battery. That is the typical alternator you would find in a typical RV, van, marine application. As soon as electricity is being generated, we don't only get electricity, we also get heat. And that heat needs to be moved out of the device, otherwise it's gonna burn up. And what they did with these alternators is they added a little fan in here When you look closely, you can see it spinning. So when it's turning the fan, and that fan moves air through the alternator out of the back here. And whenever there's a big load on this thing and the RPMs are not that high, the engine is not spinning like an idle in a traffic jam, there's not enough air being moved through this thing. And that's where they typically overheat and reduce the output in order to stay cool enough. And that's where these water-cooled alternators come in. This is our Hitachi water-cooled alternator, and it's routing coolant through these connections here through the whole device, so there's no need for any airflow. It's completely happy at idle, at full output for days, and that's why it makes it an ideal candidate for our van build, because that's what we want. We want to be able to run the air conditioner at idle, right, in a traffic jam, and we also want to be able to charge the battery when maybe just to, you know, run the motor for a half hour or 20 minutes, idle the motor to get some charge back into the battery, and that thing can do that without issues. So there's ways to also manage these alternators better. There's like a system called wake speed, and what it does, it communicates with the BMS and the rest of the vehicle and basically manages this alternator so it never really gets too hot, to avoid this kind of a, you know, scenario I described in a traffic jam, overheating. But that's very complicated, and what I don't like is there's no redundancy in that system at all. So if that thing breaks down, we're gonna run out of juice, not only for the back of our RV, but also for the rest of the car, truck. We're not gonna be able to start. Well, you know how that goes. And that's why I'm a big proponent of having two alternators, and I have converted several RVs with two alternators. I've never done a water-cooled one before. I've always just added a second air-cooled one, but this build here is the first one with a water-cooled unit, and yeah, it makes it an ideal candidate for what we plan to do. I'm pretty sure it's gonna turn out nice on the long run. So the one issue we noticed is this alternator does not need an excitation connection. Here's an extra terminal where the traditional alternator needs like a cable to receive a signal to generate energy and not. But this one here does not need that. All it takes is a battery connected and to spin, and it's gonna start to produce full power. And we realized that this is a disadvantage for our build, and that therefore I opened this thing up, and it's gonna come in the video, and added a signal line basically so we can control the energy output through a switch on the dash, turn it on and off, because we don't want this to provide full current to our battery and have the BMS basically switch off before it overcharges. That's not an ideal setup, and in the future I want to control this with a Arduino device to communicate with the BMS and basically switch that alternator off when it's at 90% charge, in that range. But for now it's gonna be fine just manually. And yeah, there's always the safety switch of the BMS as well. So we also added a diode in that alternator in order to avoid a if the BMS switches off under full load, there's going to be a voltage peak in the wiring, and that could destroy the alternator. And therefore we added a DXV diode, I think TXV. And yeah, let's do it. See you there. And now, last but not least, we're modifying our high-performance alternator here, the Hitachi, water-cooled Hitachi 190 amps alternator. And I'm gonna add a remote start for the excitation voltage, because right now, as soon as the battery is connected, the alternator starts producing, and we have no way to disable the charge current until the BMS switches off, which is not ideal because we're going to reach a peak current. And we are also adding this diode here to avoid a voltage peak if the BMS shuts off for whatever reason under full load, and we would get once the inductive field collapses in the wires, it's going to induce such a high voltage it will burn the diodes here. So we're adding this baby. Description in the link. They're very easy and cheap to buy. It just goes from positive to negative here. And yeah, this wire is usually connected to positive. And we're gonna add a switch to that so we can simply turn on and off the alternator. Well, that's the theory. We see if this is going to work or not, but yeah, probability is pretty high. Our diode is wired up, and we got our excitation cable attached. I'm just gonna route it through the opening here in the back. I'm not going to drill an extra hole. So works great because the cover is even clamping it down. And yeah, we're gonna throw it back into the car. Finished some Frankenstein modifications to our alternator bracket. That goes to the same spot where the vehicle usually has an air conditioning compressor. And we're gonna run it from there. Without this reinforcement, it was wobbling at this end here, even though it's double. So that's gonna make it strong enough for sure. So now I wanna dive into that whole plate heat exchanger idea to extract waste energy out of our air conditioner and use it for showers. And you might wonder why we did that. And there's no simple answer, but I think the best answer is, why not? I've been quite fascinated about air conditioning systems since quite a while. And not just air conditioners, but the whole physics behind it. And I've built a small hot water heater that is hooked up to a compressor fridge to basically heat up the water under the sink for washing the dish in the RV. And that works great if there's enough food in the fridge, because all that thermal energy has to come from somewhere. And what the fridge does, it sucks it out of the food and basically pumps it into my hot water to later wash dishes with. And yeah, that idea came up again when we worked on our 12-volt air conditioning system. And of course, with that, with an 800-watt air conditioner, there's much more waste heat energy that can be recovered and used for showers. And that is the whole idea behind it. So you find the test results later in the video. We already tested the output. It's not hooked up to the boiler yet. That's coming soon. Okay, I'm in Germany, the Black Forest behind me, and also our RV that received the air conditioner. And I'm gonna walk you through all the modifications that I've done or that we did in a second. Dann geht's halt, vielleicht kannst du hier durch, dass es nicht unterm Ding hängt. Alright, so the evaporator, no, sorry, the condenser fits right under the grill. The problem we had is that the original fan that came with it was way too high, the grill wouldn't fit, so just for testing purposes we added this little Honda motorcycle fan. I think that's gonna be enough for running the system in stage 1. And then if we need more power, we can use the original radiator fans that are behind here. Oh yeah, cannot see it really. So that has to be tested, and that's why obviously we used just wire to attach everything. And most likely that's gonna last a year or 2 or 3, maybe longer. My dad always said nothing lasts longer than the temporary solution. And it might be true. So we are in Italy at a campground, Cannobio Lago Maggiore. We hooked up the heat exchanger for the first time with a circulation pump. So that system, that water here is basically going to be pumped into the existing Truma heating system. And our hope is to obviously heat up the shower water with this. It has 15 liters. It's about, divided by 4, something gallons.
3.6.
3 point something gallons of water that is usually heated up by propane gas, and we want to heat it up with the air conditioning system. So the heat exchanger sits below here. Well, let me dive. We installed it right here. Yeah, you can see it now. Right here. And yeah, we'll see. We want to measure the BTUs. So we're going to measure the BTUs. We have 5 liters of water in this bucket, and we're going to drop a temperature sensor at the second run. For now, we just want to see if it works at all. So let's fire it up and see if we burn our hands after hopefully 10 minutes or so. Okay, we're about 10 minutes in here, and the water has reached about 100 and something degree. It's too hot to touch. And that's pretty cool. I can guesstimate the cooling or heating performance. Oh yeah, it's too hot now. I think we're gonna let it run another 5-10 minutes or so and see if we get it to steam. Because previously I measured the condenser temperature was almost 200 degree or 150, so that water should start steaming. And yeah, I just want to see if that really works, and then repeat that test with a proper temperature gauge later. Okay, we're back in Germany. Had a successful run, and we just swapped out another fan that fits behind the bumper here. We were just running a test of the alternator in the vehicle, And this is a temporary setup to measure the output and if our circuitry works with initiating the what's the word again? Excitation. So that's the temporary setup to test if the excitation voltage setup works. So if we can just switch the alternator on and off with that. One wire is connected to battery plus, the brown one, and that one goes to the regulator that was bolted to the plate. And this is how the whole setup looks like. Our modified bracket is up here, painted nicely black. We got an extra pulley that was for vehicles with air conditioner, so it's a double pulley, one belt just for the alternator. Awesome. Here's the tensioner. So ready to rock and roll. We'll see how many amps we get out of here, charging and running the air conditioner. I did not connect the cooling right now because I have no idea if it works or not. I don't want to go too far. We'll do that after a successful test run. Okay, here's our amp meter. Ready to test.
Soll ich anmachen?
Ja, Kontakt. Ey, setz die Batterie auf Charge. Das hast du ja noch nicht, oder?
Ja, ich habe Charge und Discharge.
Schmeiß an und dann komm raus.
Ich mache einen Gang raus, oder? Luxus.
Ja, das wäre nicht schlecht.
Okay.
Ja. Lass die Ampere außen. Nix. Wieso geht das nicht? Oh, Gas geben kurz. Amps. Nee, jetzt lädt ja. Läuft. 100 Ampere.
Ja, ja.
Halt mal. Jetzt müsst rausgehen. Okay, another test run. 5 kg of water. Circulating through our heat exchanger down there. And with that we can calculate the performance of the air conditioner. Here's our heat exchanger located. Here's our heat exchanger located. Quite tight, but fits nicely. And again, we're gonna circulate that water later through the water heater in the back while cooling the vehicle. Pretty awesome. And yeah, so we should get a roughly more than twice the input power in BTU, in heating performance. So if the air conditioner pulls 60 amps, 600 watts or 700 watts, we should have heating performance of at least 17, 18, 1900. And that's exactly what we want to find out. And we need to watch the saturation pressure, which is, we're gonna run close to 160 psi. So we should stop recording or stop measuring at 46 C, because beyond that the radiator will just deplete the energy, the heat energy that we want to get into the water. So sensor 2 is in the bucket, 16.6 Celsius. That's the cool water, the 5 kg water. Sensor 1 was what? That's the evaporator outlet.
Superheat, yeah. No. Number 1 is now superheat and number 1 is evaporator. Number 3 is this one, and number 1 is superheater.
Number 1 is
superheat.
is the evaporator outlet, and number 3 is this one in front of the evaporator, the air temperature. Okay, let's crank it up. Okay, system just kicked in. So we try to run the system just on the heat exchanger. The water is still at 20 something degree, but the high side pressure is getting out of range, high and low side pressure. So I need to kick in the fan, and that should drop now immediately. Yeah. So I just realized the plate heat exchanger is not pulling all the heat energy out of the refrigerant, because this is still way hotter than the water coming out of here, which means we cannot use this method to determine the performance. Too bad, but at least we generate hot water for free while running the air conditioner. And this is a big win. And yeah, we can still calculate how much energy goes in there in kilowatts, but I guess it's way lower than what it could be if we had a properly sized heat exchanger. The system has been running for a couple of hours now at stage 1, and the pressures are like this. So I have to add that the humidity is quite high today, around 80% I would say. So at this stage everything is fine, and yeah, we're gonna try the alternator now, because we could deplete some of the battery. The heating power is a maximum 730 watts, because the heat exchanger is not... Because the heat exchanger, to my opinion, does not have enough surface area to sufficiently cool the system. So the maximum we can get out of it is around 730 watts, while the compressor takes up 600 watts. So we are still having some net gain, because yeah, electric heater would generate 600 watts in heating power, consuming 600 watts, so we're gaining 130, which is quite good. Not as good as it could be, but enough, because you're just recovering waste energy, right? So yeah, we're gonna loop this through the Truma here, that is in the back of the RV, and I'm just gonna add some images to this video. Okay, we're gonna put the air conditioner to full power now and start the engine to see how much the alternator will generate. The battery is depleted to 84% now, so we can add some charge. Alternator is off. Kannst du ein bisschen Gas geben? So that is just the yeah, now it's. Okay, we just switched on charging for the battery. 60 amp goes into the air conditioner and 60 amps into the battery. It's perfect. So it can push 122 just in idle. I will increase the RPM a little bit. Kannst du das mal filmen hier? Okay, 190. Wow. That's what's going into the battery. Beautiful. Cannot ask for more, huh? Now, let's get to the bottom of all of this. Was it worth it to install this 12-volt air conditioner in our little RV? And the verdict is absolutely. It cooled our cabin while driving more than what we expected it would. Even on stage 1 on a hot day in Italy, it runs silently, pulls only like 30-40 amps at stage 1. So our 628 amp hour battery is gonna last easily through an entire night. And the unit was relatively easy to install. Of course, it's a bit more involved than a roof-mounted unit where you just cut a hole and dump it in. But the fact we could spread it through the entire car and decide where to put the evaporator, where the cold air comes out, is a huge plus, if you ask me. So now we have that evaporator in the cabin, and we can close the cabin with a curtain while driving. And at night, we can just add a duct and put the cold air to the back of the RV, which should work fine. If you have a 12,000 BTU unit on your RV and it's barely keeping up, this little 12-volt unit is not gonna cut it for you, because it just has 7,500 BTU, not 12 or 15,000 like most roof-mounted units. So don't believe whatever they say in the advertisement or those videos promoting these things. You see people going to Death Valley in full sunshine, running this air conditioner and claiming it's cooling down their vehicle. Well, if it's that well insulated and 7,500 BTU are enough to do that, okay, but most RVs are not, or are larger than that. So I think the sweet spot for those air conditioners are vehicles, small vans, or like campers like we have, maybe up to 25 feet, in a climate that is not too crazy hot and humid like in Florida or Texas. Or you just want to use it at night while sleeping, that's for sure gonna do it. The output at the end is similar to a small window air conditioner for a bedroom. And yeah, if you keep that in mind, it's an awesome unit. Again, don't expect it to cool your RV to a comfortable temperature in the middle of the day in full sunlight. That's not gonna do it. Our plate heat exchanger was a semi-success. We recovered waste heat, but not even half of what I expected, because I just bought the next cheapest thing, and that one was too small. It has 30 plates and it should be one with 60 plates. I ran it through AI. The figures are clear, so that's gonna come up in my next build. The air conditioner, no, sorry, the alternator was a full success. Nothing wrong there. It's very good solution for people that want to use this air conditioner while driving their RV. So very interesting for vans and older RVs that came without a factory air conditioner mounted to the engine. Yeah, that's my 2 cents to that. Or in case you just want to go full electric, then it makes perfect sense to have a second alternator just for the redundancy. And of course the speed to charge the battery bank up is totally different with a dedicated alternator that is only there to fill up the battery. Yeah, so I'm right and I'm wrong. If you're interested in more content, hit like and subscribe, and see you in the next video. I just hiked up this mountain here and I want to share the view with you. So that was a full 360. Again, I hope to see you next time.